Hello there, and welcome to Simple Science for Sleep. Tonight, we're diving beneath the waves into a world of silent giants. Right now, somewhere in the ocean, a submarine is gliding through darkness deeper than mountains are tall. These vessels move through water so quietly that whales swimming nearby can't hear them. A submarine, the length of 2 football fields, creates less sound than a whisper. It's a machine that weighs as much as a small building. Yet, it disappears into the deep like smoke. This is your place for calm curiosity. Tonight, we'll explore these peaceful machines of the deep, discovering how humans learned to live underwater. So find your comfortable spot. Let your body settle. Let's begin where it all started, with a simple question that changed everything. Imagine standing on a beach 3,000 years ago. You watch a fish leap from the water, then vanish beneath the surface. It's gone to a place you cannot follow. The fish can breathe down there. You cannot. This simple fact haunted humans for thousands of years. The ancient Greeks told stories about it. They spoke of heroes who could breathe underwater, of gods who walked the ocean floor. But these were just stories. The reality was harder. A person could hold their breath and swim down, but only for a minute or two. Then, the burning in the lungs would force them back up. Some people got better at it. Pearl divers in Japan and Korea trained their whole lives. They could hold their breath for 3 minutes, sometimes 4. They would sink down to the bottom, grab oysters or seaweed, then kick back to the surface. Their lungs were strong like drums, but even they had limits. The deep ocean stayed beyond reach. Then there was Alexander the Great. History tells us he conquered most of the known world. But there's another story about him, one that might not be true, but shows us something important. The story says he wanted to see the bottom of the sea, so his craftsmen built him a glass barrel. They sealed it tight and lowered it into the water with Alexander inside. Did this really happen? Probably not, but people told the story for hundreds of years. And that matters. It shows us that humans have always dreamed of going under. We've always wanted to see what's down there in the dark. The dream lived in people's minds for centuries. Artists drew pictures of underwater boats. Writers described vessels that could sail beneath the waves. Leonardo da Vinci sketched designs for diving equipment. But dreams and drawings aren't the same as real things. The ocean kept its secrets. What made it so hard? The problems were simple to understand, but difficult to solve. First, you needed air to breathe. Second, the water pushed in from all sides with crushing force. Third, you needed to see where you were going. Fourth, you had to move through water somehow. And fifth, you needed to get back to the surface. Every solution to one problem created new problems. Bring air down in a container. The container had to be strong enough not to break under pressure. Make the walls thick enough to resist pressure. Now, the whole thing was too heavy to move. Each answer opened new questions. But humans are stubborn creatures. We don't give up on our dreams easily. Someone, somewhere, would figure it out. And they did. If this brings you calm, consider joining our community of fellow science lovers who explore the deep mysteries of our world together. Where are you listening from tonight? What time is it there? It's wonderful to have you here as we discover these stories together. The breakthrough came from an unlikely place, not from a great scientist or a famous inventor. It came from a young man in America who wanted to help his country win a war. His name was David Bushnell, And in 1775, he built something the world had never seen before. It was small. It was strange looking. It barely worked. But it was real. It was a submarine. And it changed everything about what humans thought was possible. Let's meet the turtle. The year was 1775. America was at war with Britain. The British had powerful warships blocking American harbours. These ships were massive, made of thick oak, armed with dozens of cannons. They seemed impossible to defeat. David Bushnell was a student at Yale College. He was studying science and mathematics, but he kept thinking about those British ships sitting in the harbour. And he had a strange idea. What if you could attack a ship from underneath? What if you could swim under the water where they couldn't see you coming? People thought he was crazy, but Bushnell started building anyway. He built his submarine from oak wood, shaped like two turtle shells pressed together. That's why people called it the Turtle. It was small, very small. Only one person could fit inside, and just barely. You had to squeeze yourself in through a hatch on top, then pull the hatch shut above your head. Picture it. You're sealed inside a wooden egg standing upright. The space is so tight, your shoulders touch the sides. Above your head is the closed hatch. Around you is curved wood. And outside, through that wood, is the ocean pressing in from every direction. Inside the turtle were pedals and cranks everywhere. To move forward, you turned a crank with your hands. This spun a propeller behind you. To go up or down, you used a different crank that controlled a propeller on top. To turn left or right, you used another handle. It was like trying to ride 3 bicycles at once while sitting in a barrel. The turtle moved slowly, very slowly. A person could swim faster. When you cranked as hard as you could, the submarine barely moved forward. The water was thick and heavy. Moving through it took enormous effort. After just a few minutes of cranking, your arms burned with exhaustion. But here's the beautiful part. It worked. The turtle could actually go underwater. Bushnell had solved the basic problem that had stumped people for thousands of years. How did he do it? The answer was simple and clever. At the bottom of the turtle were tanks that could fill with water. When you opened a valve, ocean water rushed in. The turtle got heavier and sank. When you wanted to rise, you used a hand pump to push the water back out. The turtle got lighter and floated up. It was like breathing. Take in water to go down. Breathe out water to go up. For air, Bushnell added tubes that stuck up above the water when the turtle was at the surface. You could open these tubes and fresh air would come in. Then you'd close them before diving. The air trapped inside was enough to breathe for about 30 minutes. After that, you had to surface and open the tubes again. The British ship, HMS Eagle, sat in New York Harbour. It was September 1776. A soldier named Ezra Lee volunteered to pilot the Turtle. They towed the little submarine out into the harbour at night. Then Lee climbed inside, closed the hatch, and began cranking. He made it all the way to the Eagle. He positioned the Turtle underneath the ship's hull. The plan was to attach a bomb to the bottom of the ship using a screw. Lee turned the handle to drill into the wood, but the drill hit metal instead. The British had covered that part of the hull with copper plates to prevent barnacles. The drill couldn't go through. Lee tried different spots, but couldn't find wood. His air was running low. His arms were exhausted from cranking. Dawn was coming, so he gave up and cranked his way back to shore. The mission failed. The Eagle sailed away unharmed. The Turtle never sank any ships. But here's what matters. Bushnell proved something incredible. Humans could build a machine that goes underwater. A person could climb inside, seal themselves in, and survive beneath the surface. It was possible. The dream was real. The turtle was crude and clumsy. It barely worked. It looked ridiculous. But it opened a door. It showed the path forward. After Bushnell, other inventors knew submarines weren't just fantasy. They were real things that real people could build. The wooden egg that looked like a turtle taught us our first lesson about living underwater. You don't need something perfect. You just need something that works. The turtle worked just enough to prove the impossible was actually possible. And that changed everything. Now we know submarines could exist. But knowing something is possible and making it practical are two different things. The next challenge was bigger. How do you breathe down there for hours instead of minutes? How do you stay under long enough to actually do something useful? The answer would come from understanding the invisible air around us. Air is strange when you think about it. You can't see it. You can't touch it. But you need it every few seconds, or you die. This invisible thing keeps you alive. Early submarines had a simple problem. They carried air inside, sealed in with the crew, but people use up air. Every breath takes in oxygen and breathes out carbon dioxide. The oxygen gets lower, the carbon dioxide gets higher. After a while, the air becomes poison. The turtle only had 30 minutes of air. Other early submarines weren't much better. An hour, maybe 2, if you stayed very still and breathed slowly. Then you had to surface or suffocate. This made submarines almost useless. You couldn't go anywhere or do anything meaningful in such a short time. Scientists studied the problem. They learned that air is actually a mixture of gases, mostly nitrogen, which your body doesn't use, about 20% oxygen, which you need, and tiny amounts of other things. When you breathe, you pull oxygen out of the air and add carbon dioxide back into it. So submarines needed 2 things. First, add fresh oxygen. Second, remove the carbon dioxide. Simple to say, harder to do. The breakthrough came from chemistry. Scientists discovered certain chemicals that could grab carbon dioxide out of the air. Soda lime was one. It's a white powder made from calcium and sodium. When carbon dioxide touches soda lime, they stick together. The carbon dioxide gets trapped in the powder. The air becomes clean again. Picture large metal boxes filled with this white powder. Air from the submarine flows through the boxes. The carbon dioxide sticks to the powder. Clean air comes out at the other side. These boxes are called scrubbers because they scrub the air clean. But scrubbers only solve half the problem. They remove the bad gas, but don't add the good gas. The oxygen level still drops. People still suffocate, just more slowly. Early submarines carried oxygen in tanks, compressed and squeezed tight. When the oxygen level dropped, someone would open a valve and release more oxygen into the air. You had to be careful. Too little oxygen and people got dizzy and faint. Too much oxygen and things became dangerous. Oxygen makes fires burn incredibly fast. A small spark in too much oxygen could create an inferno. Submarines developed systems to measure the air constantly. Sensors checked the oxygen level, the carbon dioxide level, even the humidity. Crews learned to read these numbers like doctors reading vital signs. The air had to stay in a narrow range. Not too much of anything, not too little. Modern submarines do something even more amazing. They make their own oxygen from seawater. The process is called electrolysis. It sounds complicated, but the idea is simple. Water is made of hydrogen and oxygen stuck together. The chemical formula is H2O, 2 hydrogen atoms, 1 oxygen atom. Electrolysis uses electricity to split water molecules apart. The hydrogen goes one way, the oxygen goes another way. You collect the oxygen and release it into the submarine's air. The hydrogen gets vented outside or used for other purposes. Think about that. A submarine takes in seawater. It uses electricity to break the water into pieces. It keeps the oxygen for people to breathe. The ocean becomes an endless supply of air. As long as you have electricity, you have oxygen. Nuclear submarines can do this for months without surfacing. They generate electricity from nuclear reactors. The reactors can run for years without refueling. So, these submarines have essentially unlimited air. The ocean provides it. The reactor provides the power to extract it. The air on a submarine gets recycled over and over. The same oxygen atoms might go through your lungs dozens of times. You breathe them in. They enter your blood. They help your cells make energy. Then you breathe them out as carbon dioxide. The scrubbers catch the carbon dioxide. The electrolysis system breaks apart water and adds fresh oxygen. Round and round it goes. This recycled air smells different from normal air. It has a metallic tang, a hint of oil and machinery. People describe it as sterile, clean, but not fresh. After weeks underwater, crews forget what real air smells like. Then they surface, and the natural air smells strange and overwhelming. Too many scents. Too much pollen and dust. Their lungs expect the clean, sterile air of the submarine. The invisible air that surrounds you right now has traveled through countless lungs before reaching you. Wind carries it around the planet. Rain washes it. Plants refresh it. But on a submarine, the same small bubble of air stays with you. It becomes your atmosphere, your personal piece of sky, sealed in steel, traveling through the deep. Breathing solved. But the ocean had other challenges waiting. The deeper you go, the heavier the water becomes. And weight, as submarines would learn, is a force that crushes. Stand in a swimming pool. Put your hand flat on the surface of the water. Now push down. The water pushes back. It resists. This resistance is pressure. Now go deeper. Walk down the pool steps until the water reaches your chest. You feel it pressing against you from all sides. Your chest feels tight. Taking a deep breath requires more effort. The water is squeezing you gently. This happens because water has weight. Every bit of water above you is pressing down. At the surface, there's no water above you, so there's no extra pressure, just normal air pressure. But go down even a few feet, and the weight starts to add up. Here's the number that matters. Every 33 feet down, the pressure increases by 1 atmosphere. An atmosphere is the amount of pressure the air creates at sea level. It's what you feel right now, sitting wherever you are. Your body is built for it. You don't even notice it. Go 33 feet underwater and the pressure doubles. Now you have 1 atmosphere from the air above the ocean, plus 1 atmosphere from the water. Go down another 33 feet and it doubles again. Every 33 feet adds another atmosphere of crushing force. At 300 feet deep, the pressure is about 10 atmospheres. That's 10 times the pressure you feel right now. At 1,000 feet, it's 30 atmospheres. The water is pressing in with 30 times normal force from every direction at once. What does this do to things? It crushes them. Take a styrofoam cup and bring it down to 1,000 feet. The pressure squeezes it until it's smaller than your thumb. The air pockets in the foam get compressed into almost nothing. Take a plastic bottle down there, and it crumples like someone stepped on it. A submarine at 1,000 feet has water pressing against its hull with millions of pounds of force. If the hull has even a small weak spot, the water will find it. The metal will buckle inward. Water will spray through the gap with the force of a cutting torch. The submarine will flood and sink in seconds. So how do submarines survive this crushing pressure? The answer is shape and thickness. First, the shape. Submarine hulls are cylindrical. They're long tubes with rounded ends. This shape is crucial. A cylinder distributes pressure evenly around its surface. When water pushes in from all sides equally, the force is balance. The cylinder doesn't have flat surfaces that want to cave in. Every point on the hull is curved, and curves are strong. Think of an egg. You can squeeze an egg between your palms, and it won't break easily. The curved shell distributes the pressure, but tap it with a fork, and it cracks immediately. Curves spread force. Corners concentrate it. Submarine hulls have no corners. Second, the thickness. Submarine hulls are made of special steel several inches thick. On deep-diving submarines, the hull can be 6 inches thick or more. That's solid steel, incredibly heavy, incredibly strong. The hull isn't just one layer either. Many submarines have a double hull. The outer hull gives the submarine its shape. The inner hull, called the pressure hull, holds the air and crew. Between them is empty space. This design provides extra protection and places to store equipment. The pressure hull has to be perfect. Every weld has to be flawless. Every joint has to be tested. One flaw and the ocean will exploit it. Submarine builders inspect every inch of the pressure hull multiple times. They use X-rays to see inside the welds. They test with pressurized water to simulate deep dives. When a submarine goes deep, the crew can hear the hull adjusting. The metal creaks and groans. It's the sound of steel compressing under enormous force. The hull actually gets slightly smaller as the pressure increases. The submarine at depth is fractionally smaller than the submarine at the surface. The metal squeezes together like a spring being compressed. This sound terrifies new crew members. They hear the groaning metal and think the submarine is about to implode. But experienced sailors know these sounds are normal. It's the hull doing its job, flexing slightly to accommodate the pressure. A submarine that goes deep without making any sound would actually be more concerning. That might mean the hull is too rigid, unable to flex, more likely to crack. The deepest any military submarine can go is classified information, but we know some can dive below 1,000 feet. Research submarines have gone much deeper. The deepest parts of the ocean, nearly 7 miles down, have been visited by specially designed submersibles with hulls like steel spheres, the strongest shape nature knows. But most submarines don't need to go to crushing depths. They operate at a few hundred feet, where the pressure is strong but manageable, deep enough to hide, shallow enough to survive. The ocean is patient. It waits for mistakes. But a well-made submarine hull can hold back the weight of the world above it, creating a small bubble of normal pressure inside, where humans can live and breathe and work as if they were on the surface. Now we have air to breathe and walls that won't crush. But how does a submarine control whether it sinks or rises? How does it find that perfect depth and stay there, floating in the middle of the ocean like a bubble suspended in a glass of water? Drop a rock in water and it sinks. Drop a piece of wood, and it floats. The difference is density. The rock is heavier than the same amount of water. The wood is lighter. Dense things sink. Light things float. A submarine needs to do both. It needs to sink when you want it to sink, float when you want it to float, and sometimes it needs to hover right in the middle, neither rising nor falling. This is the art of ballast. Ballast means weight you can add or remove. Ships have used ballast for thousands of years. They'd load heavy stones into the bottom of the ship to keep it stable. Need the ship lighter to cross a shallow river? Remove some stones. Need it heavier for stability in a storm? Add more stones. Submarines use water as ballast. But instead of loading and unloading it like stones, they use tanks that fill and empty. These ballast tanks are built into the submarine's hull, large spaces between the inner pressure hull and the outer hull. When a submarine wants to dive, valves open at the bottom of the ballast tanks. Water rushes in. Air that was in the tanks escapes through vents at the top. The submarine gets heavier. It sinks. When the submarine wants to surface, compressed air blows into the ballast tanks. The air pushes the water out through the bottom valves. The submarine gets lighter. It rises. It's elegant, simple, like breathing. Take in water to go down. Release water to go up. The submarine becomes heavier or lighter by filling its lungs with the ocean itself. But true control requires more precision. This is where trim tanks come in. Trim tanks are smaller tanks throughout the submarine. They fine-tune the balance. If the submarine is slightly nose-heavy, you pump water from the forward trim tank to the aft trim tank. Now, the back is heavier and the submarine levels out. Submarines aim for neutral buoyancy. This is the magical point where the submarine weighs exactly the same as the water it displaces. At neutral buoyancy, the submarine doesn't want to sink or rise. It just hovers. It can stay at a specific depth without using any energy to hold position. Finding neutral buoyancy takes skill. The submarine commander adjusts trim tanks carefully. A little water here, a little air there. Testing, adjusting. When you get it right, the submarine feels weightless. It floats in the middle of the ocean, like you might float in the middle of a pool when you have just the right amount of air in your lungs. Everything on a submarine affects its buoyancy. When crew members move from one end of the submarine to the other, the trim changes slightly. When the submarine fires a torpedo, it loses weight. When it takes on supplies, it gains weight. The trim has to be constantly adjusted. Even the density of the water matters. Salt water is denser than fresh water. A submarine traveling from the ocean into a river has to adjust its ballast. The water around it is lighter now, so the submarine needs to become lighter too, or it will sink. Temperature changes water density as well. Cold water is denser than warm water. A submarine moving through layers of different temperature has to keep adjusting. What worked at the surface might not work at depth, where the water is colder and heavier. There's a phenomenon called a thermocline. It's a layer in the ocean where temperature changes rapidly. Above the thermocline, the water is warm. Below it, the water is cold. Submarines can hide beneath thermoclines because sonar doesn't pass through them well. But crossing a thermocline requires careful buoyancy control. The density change can be abrupt. Master submarine crews develop an intuition for their vessel's balance. They can feel when the trim is off. They sense when the submarine is slightly nose-heavy or tail-heavy. They make tiny adjustments constantly, keeping the submarine perfectly balanced like a tightrope walker, making small movements to stay upright. At night on a submarine, when everything is quiet, you can sometimes hear the trim tanks adjusting. A gentle whoosh of water moving from one tank to another. The submarine breathing slowly, maintaining its perfect hover in the deep. This balance is meditative. The submarine finds its depth and stays there effortlessly. No struggling, no fighting the water. Just acceptance and adjustment. Be heavy enough to stay down. Be light enough not to sink further. Find the middle way and rest there in the dark. Scuba divers know this feeling. When you've added just the right amount of air to your vest, you hang in the water without effort. You don't sink. You don't rise. You simply exist in the middle of the ocean, suspended, peaceful. A submarine at neutral buoyancy is like this, but on a massive scale. Thousands of tons of steel hanging in perfect balance. Not falling, not climbing, just being. But hovering in the dark presents another problem. How do you know where you're going when you can't see anything? How do you navigate in an ocean that has no landmarks, no roads, no signs? How do you see without light? Most submarines have no windows. This surprises people. They imagine looking out through glass at fish and coral. But windows are weak points. Glass can't withstand the crushing pressure of deep water. So submarines seal themselves completely. The crew lives inside a steel tube with no view of the outside world. So, how do they see? They listen. Sound behaves strangely underwater. In air, sound travels about 767 miles per hour. In water, it travels almost 5 times faster. Sound waves move through water more efficiently than through air. They travel farther. They carry more information. Submarines use this fact. They create sound and listen to what comes back. This is sonar. The word comes from sound navigation and ranging. It's exactly what it sounds like. Using sound to navigate and measure distance. Active sonar works like shouting in a cave. The submarine sends out a pulse of sound, a ping. This sound wave travels through the water in all directions. When it hits something solid, the sound bounces back. The submarine sensors detect this echo. By measuring how long the echo took to return, they calculate distance. A quick return means the object is close. A delayed return means it's far away. The direction the echo comes from tells you where the object is. The strength of the echo tells you how big it is and what it might be made of. Metal reflects sound differently than rock. A whale sounds different than a ship. But active sonar has a problem. When you ping, everyone can hear you. It's like turning on a flashlight in a dark room. Yes, you can see, but everyone else can see you too. For military submarines trying to stay hidden, active sonar defeats the purpose. So submarines mostly use passive sonar. They listen without making sound. The ocean is not silent. It's full of noise. Waves on the surface create rumbling. Marine life clicks and calls. Ships and submarines create mechanical sounds. Their engines hum. Their propellers churn water. Metal components vibrate. Passive sonar arrays are lines of sensitive microphones. They pick up these sounds. Computer systems analyze them. Each type of vessel has a unique sound signature. A Russian submarine sounds different from an American one. A cargo ship sounds different from a fishing boat. Experienced sonar operators can identify vessels by their sound alone, the way you might recognize a friend's voice on the phone. The sonar room on a submarine is quiet. Operators wear headphones. They sit in dim light, listening intently. They hear the ocean breathing. Distant ships passing far away sound like faint whistles. Closer vessels create deeper thrums. The sound of rain on the surface creates a soft static. Whales singing miles away come through as haunting melodies. Sonar operators describe it as seeing with your ears. After months of training, they build mental maps from sound. They know, without looking, that a fishing boat is 2 miles to the north. A whale pod is swimming east. Another submarine is lurking somewhere to the south, trying to stay quiet, but betrayed by a slight mechanical hum. Sound layers in the ocean. It doesn't travel in straight lines. Temperature and salinity affect how sound bends. Warm water on top and cold water below create a channel where sound gets trapped. This channel can carry sound for hundreds of miles. 2 submarines on opposite ends of this channel might hear each other perfectly, while submarines above or below the channel hear nothing. There are also shadow zones where sound doesn't reach. A submarine can hide in these zones, invisible to sonar. Thermoclines, those temperature layers we talked about earlier, reflect sound. A submarine can hide beneath a thermocline like hiding behind a soundproof wall. The deep ocean has its own strange sounds. Sometimes sonar picks up noises nobody can explain. Low-frequency rumbles, high-pitched whistles. Some are probably geological. Underwater earthquakes, volcanic activity. Others might be creatures we haven't discovered yet. The ocean is vast and mostly unexplored. Who knows what's down there making noise? Submarines also use other navigation tools. Inertial navigation systems track every movement the submarine makes. They measure every turn, every acceleration, every change in depth. Starting from a known position, they calculate where the submarine is now based on all its movements. It's like counting steps to know how far you've walked. GPS doesn't work underwater. Radio signals that GPS satellites send can't penetrate water. So submarines navigate using sonar, inertial systems, and charts. Sometimes they raise a periscope or communications mast to the surface to get a GPS fix. Then they descend again with updated position information. The periscope itself is rarely used now. Modern submarines use photonics masts with cameras instead. Safer, harder to spot, but the concept is the same. Poke something above the surface. Look around quickly. Get back down before anyone sees you. Navigation underwater is an art of patience. You move slowly. You listen carefully. You build your picture of the world from echoes and memories and calculations. You trust your instruments and your training. And you stay quiet. Always quiet. Because in the deep ocean, sound is both your eyes and your vulnerability. Silence is survival for a submarine. The quieter you are, the harder you are to find. The louder you are, the easier you die. So submarines obsess over noise. Every sound is a potential death sentence. A submarine makes noise in countless ways. The propeller spinning creates turbulence. Machinery vibrates against the hull. Pumps circulate water. Fans move air. People walk. Doors close. Every tiny sound can travel miles through water. Engineers have spent decades learning how to silence submarines. The result is some of the quietest machines humans have ever built. A modern submarine can pass within a mile of you, and you'd never know it was there. Let's start with the hull. The outside of a submarine is covered in special tiles. They look like thick rubber. These tiles serve 2 purposes. First, they absorb sound. When noise from inside the submarine tries to escape, the tiles soak it up. Second, they absorb incoming sonar pings. When another submarine sends out active sonar, the tiles prevent strong echoes. The submarine becomes acoustically invisible. These tiles are called anechoic coating. The word means without echo. Each tile contains thousands of tiny air pockets. Sound waves enter the tile and bounce around inside these pockets, losing energy. The sound dissipates as heat. What should be a clear echo becomes a whisper. Inside the submarine, machinery mounts on special springs and rubber isolators. Think of a car's suspension system. When you drive over a bump, the springs absorb the shock so you don't feel it. Submarine machinery works the same way. A pump might vibrate, but the vibration stays in the springs. It doesn't reach the hull. It doesn't transmit into the water. The propeller is one of the hardest things to quiet. When propeller blades spin through water, they create regions of low pressure behind them. Water can't sustain very low pressure. It boils, even when cold. These tiny bubbles form and immediately collapse. This is called cavitation. Each collapsing bubble makes a tiny pop. Thousands of bubbles collapsing per second create a roar. Modern submarine propellers are carefully designed to minimize cavitation. The blades have special shapes. They spin at precise speeds. Some submarines use pump jets instead of propellers. A pump jet is enclosed in a tube. Water flows through it more smoothly. Less turbulence, fewer bubbles, less noise. The slowest submarines are the quietest. Speed creates noise. Water rushing past the hull makes sound. Faster speeds create more turbulence. So submarines trying to hide move at just a few knots. Walking speed, slower than you jog. They creep through the ocean like ghosts. Everything on a submarine is built with noise in mind. Hatches close on rubber seals. Tools have padded handles. Heavy objects rest on rubber mats. Crew members wear soft-soled shoes. They learn to move gently. No slamming. No dropping things. Every action is deliberate and quiet. There's even a condition called ultra-quiet mode. When a submarine detects another submarine nearby, it goes ultra-quiet. Non-essential machinery shuts down. People stop moving unless necessary. Conversations happen in whispers. The submarine becomes as silent as a tomb. It hovers in the water, barely breathing, hoping the other submarine passes by without detecting it. During ultra-quiet mode, you can hear your own heartbeat. The normal background hum of machinery vanishes. The silence becomes oppressive. Crew members describe it as eerie. You become aware of every sound your body makes. Breathing seems loud. Swallowing seems loud. Your joints cracking sounds like gunshots. This silence can last hours. Everyone stays at their stations, barely moving, waiting. The tension builds. Everyone knows that if the other submarine detects them, there might be consequences. In peacetime, it's embarrassment. In wartime, it could be worse. Some submarines are quieter than the background noise of the ocean itself. They produce less sound than the ambient crackling of snapping shrimp, the rustling of sand on the seafloor, the distant rumble of surface waves. They become acoustically indistinguishable from the ocean. They disappear into the sonic landscape. The United States and Russia spent decades in an acoustic arms race, each side trying to make quieter submarines and better sonar to detect the other side's quiet submarines. Billions of dollars invested in shaving off a few decibels of noise. The race continues today, though fewer people talk about it. China now builds submarines too. Their early models were noisy, easy to track, but their newer submarines are much quieter. The technology spreads. Knowledge leaks. What was cutting edge yesterday becomes standard today. Silence underwater requires obsessive attention to detail. Every component, every system, every human action, all designed around one principle. Don't make sound. Disappear. Become nothing but a shadow in the deep. The irony is beautiful. These massive machines, weighing thousands of tons, moving through water, powered by nuclear reactors or diesel engines, can be quieter than a whisper, quieter than a leaf falling, quieter than your breath as you fall asleep. But submarines aren't just about hiding. They're also about living. And living in a steel tube underwater for months requires solving some very human problems. Imagine living in a hallway. A narrow hallway packed with equipment. That's what a submarine feels like. Pipes run along the ceiling. Cables snake along the walls. Machinery fills every corner. The spaces between are where people live. A typical submarine might be 300 feet long, but only 30 feet wide. Most of that space is equipment, weapons, reactors, ballast tanks. The crew quarters occupy a fraction of the total volume. Maybe 100 people living in a space the size of a small house. Privacy doesn't exist. Personal space doesn't exist. You're always inches from someone else. Always hearing other people breathe. Always aware of others moving nearby. It sounds claustrophobic. For some people, it is. They can't handle it. They wash out of submarine training. But others adapt. They learn to find peace in the closeness. The submarine becomes a shared home. Your crewmates become family. You learn everyone's habits. You know who snores, who talks in their sleep, who wakes up grumpy, who tells jokes. These people are your world for months. Sleeping quarters are stacked bunks, 3 high in most spaces, sometimes 4. The bunks are narrow, just wide enough for one person, about 6 feet long, maybe 2 feet of clearance above you. You climb into your bunk, and there's a curtain you can pull for a tiny bit of privacy. On many submarines, there aren't enough bunks for everyone. They use a system called hot bunking, when one crew member finishes their shift and gets out of bed. Another crew member on the opposite shift climbs into the same bunk. The bed never gets cold. It's always warm from the last person. 3 people might share one bunk, sleeping in rotation. At first, this seems terrible, but submarine crews say you get used to it. Your body learns to sleep in any conditions. The gentle vibration of the submarine becomes comforting. The white noise of ventilation systems becomes a lullaby. Many submariners report sleeping better underwater than on land. On land, there's too much quiet, too much variation. Underwater, the sound is constant and predictable. Time works differently on a submarine. There's no sunrise or sunset, no natural cycle of day and night. The submarine creates its own time. Many submarines run on 18-hour days instead of 24-hour days. 6 hours on duty, 12 hours off duty. This 18-hour cycle somehow works better for submarine operations than a normal day. But your body doesn't know it's an 18-hour day. Your circadian rhythm expects 24 hours. This creates a constant slight jet lag. You're always a bit off. Some people adapt quickly. Others struggle with it for the entire deployment. Meals become important rituals. The galley is small, but the food is often surprisingly good. Submarine cooks are specially trained. They know how to make tasty meals with limited ingredients. Fresh food doesn't last long underwater. After the first week or 2, it's all canned and frozen. But good cooks can work magic with it. Everyone eats together when they can. Meals are social time, a chance to relax and talk about something other than work. The galley might have a few tables where crew members gather. They share stories. They complain about minor annoyances. They joke around. These moments of normalcy matter. Exercise happens in tight spaces. Some submarines have a small gym, maybe a treadmill, some weights, but mostly people improvise. Push-ups between equipment, pull-ups on pipes, anything to move your body and burn energy. Physical activity helps manage stress. It helps you sleep better. It keeps your body from atrophying in the confined space. Hygiene is interesting. Fresh water is limited on some submarines. Others can make as much fresh water as they need from seawater. But even with unlimited water, showers are kept short. 2 minutes. Get wet. Soap up. Rinse off. Done. No lingering under hot water. That would be wasteful. Laundry facilities exist, but they're small. You might do laundry once a week. Some crew members bring extra clothes. Others wear things multiple times. The submarine has a particular smell, a mix of oil, cleaning products, recycled air, and human bodies in close quarters. After a few days underwater, you don't notice it anymore. But when you surface, fresh air smells strange and overwhelming. Entertainment is low-tech. Books are popular. Many submariners read voraciously. Movies on laptops or shared screens. Card games. Board games. People bring hobbies. Someone might practice guitar quietly in a corner. Someone else might draw. Others write letters home, even though they can't send them until they surface. Communication with the outside world is limited. On some deployments, you can send brief familygrams, short messages to and from family, 20 words maximum, no details about where you are or what you're doing. Just, I'm okay, I love you, talk to you when I get back. Other deployments have no communication at all, complete radio silence for months. Your family knows you're somewhere underwater, but nothing else. They wait and trust that you're safe. This isolation creates bonds. Your crewmates are all you have. You depend on each other completely. If something goes wrong, they're the only ones who can help. There's no calling for backup. No emergency services. Just you and them against the ocean. People handle it differently. Some thrive. They love the simplicity. No bills to pay. No traffic to sit in. No outside stresses. Just your job and your crew. Others struggle. They miss the surface. They miss sunlight. They count down the days until they can go home. But whether they love it or hate it, everyone adapts. Humans are remarkably flexible. Give us a steel tube underwater, and we'll find ways to make it livable. We'll create routines and rituals. We'll build community. We'll make it home. Fresh vegetables don't last long underwater. Lettuce wilts. Tomatoes get soft. Apples lose their crunch. Within 2 weeks, most fresh produce is gone. You're left with canned and frozen food, nutritious but monotonous. The same textures, meal after meal. Some submarines have found a solution. They grow food on board. Small gardens under LED lights. It sounds impossible. Growing plants in a steel tube deep underwater. But it works. The gardens are tiny, maybe a few square feet of growing space. Hydroponic systems where plants grow without soil. Their roots sit in nutrient-rich water. LED lights provide the energy plants normally get from the sun. The lights glow with a purple-pink color, combining the red and blue wavelengths that plants need most. What do they grow? Mostly quick-growing greens, lettuce, herbs, sometimes small tomatoes or peppers. Nothing that takes months to mature. Submarines can't wait that long. They need plants that go from seed to harvest in weeks. The smell is what matters most. When you open the door to the small growing area, the scent of living plants fills the air. It's earthy and fresh. It smells like the surface world. In a submarine, where everything smells like metal and recycled air, this natural smell is precious. Crew members volunteer to tend the plants, checking them daily, making sure the water level is right, adjusting the lights. It becomes a meditation, a way to disconnect from the intensity of submarine operations. You spend 15 minutes with the plants, and your stress melts away. The harvest is small but meaningful. Maybe enough lettuce for one salad per crew member every few weeks. A handful of fresh herbs to add to a meal. It's not about the quantity. It's about the connection. These plants are alive, growing, changing. Everything else on the submarine is static, mechanical, unchanging. But the plants are dynamic. They're a reminder that life continues even here in the deep. Psychologists have studied this. They found that access to growing plants improves mental health on long deployments. People report feeling calmer, less stressed, more connected to something beyond the submarine. The simple act of caring for a living thing provides purpose and routine. Some submarines take it further. They grow microgreens, tiny shoots of plants harvested when they're only a few inches tall. These grow incredibly fast. 7 to 10 days from seed to harvest. They're packed with nutrients. A handful of microgreens contains vitamins and minerals that would fill a multivitamin pill. The crew looks forward to harvest days. Word spreads quickly. The basil is ready. We're cutting lettuce tonight. People get excited about something that on land would be mundane. A few leaves of fresh lettuce? Who cares? But here, underwater, months from any farm or garden, those leaves are treasure. There's also symbolic meaning. These plants shouldn't be able to grow here. There's no soil, no rain, no natural sunlight, no insects for pollination, no wind, nothing from the natural world plants evolved in. Yet they grow anyway, because humans created the conditions they need. This mirrors the submarine itself. Humans shouldn't be able to live underwater. We can't breathe water. We can't withstand pressure. We can't see in the dark. Yet we live here anyway, because we've created the conditions we need. We bring our atmosphere with us. We build walls to hold back the pressure. We make light to see by. We're like the plants, surviving in an impossible place because we've recreated home. Not all submarines have growing systems. Some don't have space. Others don't see the value. But the ones that do report benefits beyond nutrition. The gardens become a social gathering point. People stop by to look at the plants, to smell them, to check their progress. Conversations happen there. Friendships deepen. There's something hopeful about growing food underwater. It says that no matter where humans go, we'll find ways to sustain ourselves. We'll adapt our needs to the available resources. We'll create life in the most unlikely places. Astronauts on the International Space Station grow plants too, in microgravity. No up or down. No natural water distribution. Yet, they grow lettuce and flowers and experiment with other crops. The challenges are different from submarines, but the principle is the same. Create the conditions life needs, and life will flourish. The submarine gardens are also practical. Fresh vegetables combat vitamin deficiencies. They provide variety in diet. They improve digestion. But more than that, they provide hope. As long as things are growing, the future exists. Each seed that sprouts is a promise that time continues, that life persists, that there's something to look forward to. Tending plants on a submarine teaches patience. You can't rush growth. You plant the seed, provide what it needs, and wait. The plant will grow at its own pace. This patience translates to other aspects of submarine life. You learn to accept that some things take time, that you can't force outcomes, that your job is to provide the right conditions and trust the process. When crew members return home after months underwater, many start gardens. They've developed a connection to growing things. They've learned that cultivation is a form of meditation, that watching something grow brings peace. The submarine gardens create gardeners, but plants aren't the only things submarines carry with them. Every submarine needs power, and the story of how submarines generate that power is one of the most remarkable achievements in engineering. Early submarines had a frustrating limitation. They ran on batteries underwater. Batteries don't last long, a few hours at most. Then you had to surface, start diesel engines, and recharge. This meant submarines spent most of their time on the surface. They only submerged briefly when needed. They weren't really submarines. They were surface ships that could dive temporarily. True submarines needed power that lasted. Power that didn't require surfacing. Power that could run for months or years. The answer came from the heart of atoms. Nuclear power. Everything in the universe is made of atoms. Tiny particles too small to see. At the center of each atom is a nucleus, even tinier. The nucleus contains protons and neutrons, held together by powerful forces. Breaking these forces releases energy, tremendous energy, more energy than any chemical reaction could produce. Some atoms are unstable. Their nuclei want to break apart. We call these radioactive atoms. Uranium is one. When a uranium nucleus splits, it releases heat and radiation. This splitting is called fission. One uranium atom splitting isn't impressive. But when billions of atoms split every second, the heat becomes intense. A nuclear reactor controls this process. It uses uranium fuel arranged carefully. Neutrons from splitting atoms hit other atoms, causing them to split. A chain reaction, but the reaction is controlled, not explosive. Control rods absorb excess neutrons. Push the control rods in and the reaction slows. Pull them out and it speeds up. The heat from fission boils water. The steam drives turbines. The turbines spin generators. The generators create electricity. It's the same principle as a coal power plant or natural gas plant. Burn something, make heat, boil water, spin turbines, generate electricity. Except nuclear fuel contains millions of times more energy than coal or gas. A piece of uranium the size of your fingertip contains as much energy as several tons of coal. This density is what makes nuclear submarines possible. You can carry enough fuel to run for decades. Some submarines go 20 or 30 years without refueling. The reactor that powers the submarine lasts longer than most crew members' entire careers. This changes everything. A nuclear submarine can stay underwater indefinitely, months without surfacing. The only limitation is food and crew endurance. The power never runs out. The air recycling systems run continuously. The water purification systems never stop. The submarine becomes truly independent. Nuclear submarines are also fast. Diesel submarines had to conserve battery power. They crept along slowly. Nuclear submarines have abundant power. They can sprint if needed. Some nuclear submarines can travel faster underwater than most surface ships can travel on the top of the water. The reactor compartment is sealed off from the rest of the submarine. Thick shielding protects the crew from radiation. The reactor itself is surrounded by water and steel. Multiple barriers prevent any release of radioactivity. Nuclear submarines have operated for over 60 years with remarkable safety records. Accidents are rare. The systems are redundant. Safety is paramount. Crew members who work in the nuclear section receive extensive training. They learn reactor physics. They learn safety procedures. They learn how to monitor and maintain the systems. Nuclear operators on submarines are among the most highly trained technical personnel in any military. The reactor provides more than propulsion. It provides all the submarine's electricity, lights, computers, sonar, communications, cooking equipment, medical equipment. Everything runs on nuclear-generated electricity. The submarine carries enough power for a small city. This abundance creates possibilities. Remember the water electrolysis we talked about earlier? Splitting water into hydrogen and oxygen? That requires lots of electricity. Nuclear submarines have electricity to spare. They can make oxygen continuously. They can purify unlimited seawater into drinking water. They're self-sufficient in ways diesel submarines could never be. There's something profound about carrying a tiny sun inside your submarine. Because that's essentially what a nuclear reactor is. The same process that powers the sun. Nuclear fusion in the sun combines atoms. Nuclear fission in a reactor splits atoms, but both release energy from the fundamental forces holding matter together. The sun is 93 million miles away. Its light takes 8 minutes to reach Earth. But inside a nuclear submarine, you carry your own piece of stellar power, contained, controlled, providing endless energy in the eternal darkness of the deep ocean. Diesel submarines still exist. They're quieter in some ways, cheaper to build, easier to maintain. Some countries prefer them, but for long-range operations, for extended patrols, for true independence from the surface, nuclear power is unmatched. The reactor never sleeps. It runs continuously for years, generating heat, boiling water, spinning turbines, creating the electricity that keeps everything alive. It's the heart of the submarine, always beating, always warm, always providing. Standing near the reactor compartment, you can feel the warmth through the shielding. The metal is warm to the touch. It's the only warm metal on the submarine. Everything else is cool or cold, but the reactor space radiates gentle heat, like standing near a fireplace, comforting, reassuring, a reminder that the power is there, reliable and constant. This power lets submarines do things that seem impossible. It lets them travel under the Arctic ice. It lets them stay hidden for months. It lets them operate in places no surface ship can reach. And some of those places are among the strangest environments on Earth. The Arctic Ocean is covered in ice, thick ice that floats on the surface in massive sheets. Some areas, the ice is 10 feet thick. Other areas, it's 30 feet thick. Pressure ridges where ice sheets collide can tower even higher. Under this ice is an ocean. Dark, cold, quiet. Submarines have been traveling under Arctic ice since the 1950s. It's one of the most dangerous and strange environments a submarine can enter. Once you go under the ice, you're committed. You can't surface. The ice blocks your way. You're trapped beneath until you find an opening. The water under Arctic ice is cold, just above freezing, around -2 degrees Celsius. Seawater can be colder than 0 because salt lowers its freezing point. This cold makes things difficult. Equipment that works fine in warmer water can malfunction. Seals can become brittle. Systems have to be designed for extreme cold. But the cold also helps submarines. Cold water is denser. Sound travels differently through it. Submarines can hide more easily, and the ice above creates an acoustic barrier. Sonar from ships or aircraft can't penetrate the ice well. Under the ice, submarines are nearly invisible. Navigation under ice is challenging. GPS doesn't work underwater. You navigate by inertial systems and dead reckoning, calculating your position based on your speed and direction. Small errors accumulate. After hours or days under ice, you might be miles from where you think you are. Submarines use upward-looking sonar to map the underside of the ice. The ice isn't flat. It has ridges and valleys, deep keels that hang down like inverted mountains. These keels can extend 30 or 40 feet below the surface. A submarine has to avoid them. Hit one and you damage your submarine, possibly catastrophically. The sonar creates a profile of the ice above. Operators watch screens showing the ice contours. They navigate through channels of deeper water. They avoid the keels. It's like flying an airplane through a mountain range in fog, except upside down. And the mountains are ice, and they're constantly shifting because the ice moves. It's not static. Ocean currents push it. Wind drags it. Ice sheets grind against each other. Leads open up. These are cracks in the ice where open water appears. Sometimes leads are hundreds of feet wide. Other times, just a few feet. Submarines search for leads when they need to surface. Finding a lead requires patience. The submarine rises slowly, using upward sonar to find thin ice or open water. When they find a promising spot, they come up carefully, very carefully. The sail, the tower on top of the submarine, breaks through first. If the ice is thin enough, the submarine can push through it. The sail is reinforced for this, designed to break ice. The sound of breaking through ice is unforgettable. A grinding, cracking, groaning noise. The submarine rises. The ice resists. Then it shatters. Chunks of ice fall away. The submarine emerges into the frozen air above. Once on the surface, crew members can open hatches and step onto the ice, walking on top of the ocean, miles from any land, surrounded by endless white. The silence up there is absolute. No birds, no insects, no wind sometimes, just vast frozen emptiness. Scientists love Arctic submarine missions. The submarines can study the underside of the ice. They can measure ice thickness. They can collect data on ocean currents and temperature. They can study how climate change affects the ice. Some submarines carry scientists who spend weeks gathering information unavailable any other way. The Arctic is changing. The ice is melting. Areas that were frozen year-round now have open water in summer. This changes submarine operations. More open water means easier navigation, but it also means less acoustic cover, less protection from detection. Nuclear submarines are especially suited for Arctic operations. They don't need to surface for air or to recharge batteries. They can stay under the ice for months. They can travel from one side of the Arctic Ocean to the other without surfacing once. In 1958, the USS Nautilus became the first submarine to reach the North Pole underwater. It was a remarkable achievement, traveling under ice for days, navigating by instruments alone, emerging at the exact top of the world. They took photographs through the periscope, ice in every direction, the pole marked only by their calculations. Other submarines followed. They mapped the Arctic seafloor. They discovered underwater mountain ranges. They found the deepest parts of the Arctic Ocean. They proved submarines could operate anywhere, even in the most extreme environments on Earth. The experience of being under Arctic ice is surreal. You're in an enclosed space, a submarine. That enclosed space is under another enclosed space. The ice. You're doubly isolated. Two barriers between you and the sky. The feeling is both claustrophobic and oddly peaceful. The ice insulates sound. Under it, the ocean is quieter than anywhere else. No surface noise. No ship traffic in most areas. Just the submarine and the cold and the ice. It's the most remote place humans regularly visit. More isolated than the desert. More isolated than the deep jungle. You're under the ice. Under the ocean. In a steel tube. Farther from help than almost anywhere else on the planet. Yet submarines have operated there safely for decades. They've learned the ice. They've learned how to navigate its dangers. They've turned one of Earth's most hostile environments into a place humans can work and explore. The ice teaches patience. You move slowly. You watch carefully. You don't take risks. And in return, the Arctic lets you pass through its frozen realm. A visitor in a world that never sees the sun for months at a time. Military submarines don't go very deep. Most operate between 200 and 800 feet. That's deep enough to hide. Deep enough to avoid most surface threats. But the ocean is much deeper than that. The average ocean depth is about 12,000 feet. The deepest point, the Mariana Trench, goes down almost 36,000 feet. 7 miles straight down. To explore these depths, we need different submarines. Research submarines built specifically for extreme pressure. These are smaller than military submarines. They carry only a few people, sometimes just 2 or 3. But they can go where military submarines cannot. One famous research submarine is Alvin. It's been operating since 1964. Alvin has made over 5,000 dives. It discovered hydrothermal vents on the ocean floor. It explored the wreck of the Titanic. It carried hundreds of scientists to the deep ocean to study life and geology in the abyss. Alvin can dive to about 21,000 feet. That's 4 miles down. At that depth, the pressure is incredible. Over 9,000 pounds per square inch. That's like having 3 cars stacked on every square inch of surface. The pressure would crush a normal submarine instantly. So, how does Alvin survive? Its crew compartment is a titanium sphere. Perfect sphere. Just like submarine hulls use cylinders, deep diving submersibles use spheres. A sphere distributes pressure even more efficiently than a cylinder. Every point on the surface is equidistant from the center. The forces balance perfectly. The titanium sphere is only about 6 feet in diameter. Inside, 3 people sit cramped together. Knees touching. No room to stand. No privacy. Just enough space to operate the controls and look out the small portholes. They spend hours like this. Sometimes 8 or 10 hours on a single dive. The portholes are tiny, thick acrylic plastic, several inches thick, conical shape, wider on the outside than inside. This shape helps the pressure push the window into its frame. The more pressure, the tighter the seal. The ocean actually helps keep the window in place. Looking through these portholes into the abyss is otherworldly. At 20,000 feet, it's completely dark. No sunlight reaches that deep. The submersible's lights illuminate only a small area. Beyond that circle of light is infinite blackness. You see strange creatures, fish with huge eyes, transparent bodies, bioluminescent organs that glow. Life adapted to eternal darkness and crushing pressure. The deepest anyone has ever gone is the Mariana Trench. In 1960, Jacques Piccard and Don Walsh descended in a submersible called the Trieste. They reached the bottom, 35,814 feet. They spent 20 minutes there. The pressure was over 16,000 pounds per square inch, 8 tons per square inch. The Trieste used a different design. Its pressure sphere was attached to a large float filled with gasoline. Gasoline is lighter than water and doesn't compress under pressure like air does. The float provided buoyancy. To descend, they carried iron pellets as ballast. To ascend, they released the pellets. Simple and reliable. At the bottom of the Mariana Trench, they saw something surprising. A flatfish, a living creature at the deepest point on Earth. This proved that life exists everywhere in the ocean. No depth is too extreme. Life finds a way. In 2012, filmmaker James Cameron made a solo dive to the Mariana Trench. He stayed longer than Picard and Walsh. He filmed and collected samples. His submersible, the Deep Sea Challenger, was built from special foam that could withstand the pressure. The whole vehicle was long and narrow, like a torpedo standing upright. These extreme depth dives are rare. They're expensive. They're risky. But they teach us about the limits of engineering. Each dive pushes materials science forward. We learn what works under pressure. We develop new alloys, new designs, new techniques. The pressure at extreme depths does strange things. It changes the properties of materials. Wood becomes waterlogged and heavy. Styrofoam compresses into dense pellets. Air spaces collapse. Even the water itself becomes denser. Slightly, but measurably denser than surface water. Deep-sea submersibles move slowly. They're not streamlined for speed. They're built for strength. Their movements are deliberate. Rising and sinking is controlled by ballast. Moving horizontally is done with small thrusters. Everything is gentle. No sudden movements. No rushing. The silence at depth is profound. The submersible's equipment hums quietly. Otherwise, nothing. No waves, no surface noise. Just the pressure of miles of water above you. The weight of the ocean pressing down. Scientists who dive in research submersibles describe it as meditative. The slow descent, the darkness, the strange beauty of deep-sea life. The knowledge that you're in a place very few humans have ever been. It changes your perspective, makes you realize how little we know about our own planet. Most of the deep ocean remains unexplored. We've mapped the surface of the Moon and Mars in more detail than we've mapped our ocean floor. Deep-sea submersibles are slowly changing that, dive by dive, discovery by discovery. These submarines prove that depth is not a barrier. Pressure is not a limit. With the right design, the right materials, the right preparation, humans can go anywhere, even to the deepest, darkest places on Earth. But whether diving to extreme depths or cruising at moderate depths, all submarines share certain challenges. One of the most basic is something we take for granted on land: temperature. Military submarines don't go very deep. Most operate between 200 and 800 feet. That's deep enough to hide, deep enough to avoid most surface threats. But the ocean is much deeper than that. The average ocean depth is about 12,000 feet. The deepest point, the Mariana Trench, goes down almost 36,000 feet, 7 miles straight down. To explore these depths, we need different submarines. Research submarines built specifically for extreme pressure. These are smaller than military submarines. They carry only a few people, sometimes just 2 or 3, but they can go where military submarines cannot. One famous research submarine is Alvin. It's been operating since 1964. Alvin has made over 5,000 dives. It discovered hydrothermal vents on the ocean floor. It explored the wreck of the Titanic. It's carried hundreds of scientists to the deep ocean to study life and geology in the abyss. Alvin can dive to about 21,000 feet. That's 4 miles down. At that depth, the pressure is incredible. Over 9,000 pounds per square inch. That's like having 3 cars stacked on every square inch of surface. The pressure would crush a normal submarine instantly. So how does Alvin survive? Its crew compartment is a titanium sphere. Perfect sphere. Just like submarine hulls use cylinders, deep-diving submersibles use spheres. A sphere distributes pressure even more efficiently than a cylinder. Every point on the surface is equidistant from the center. The forces balance perfectly. The titanium sphere is only about 6 feet in diameter. Inside, 3 people sit cramped together, knees touching. No room to stand, no privacy. Just enough space to operate the controls and look out the small portholes. They spend hours like this, sometimes 8 or 10 hours on a single dive. The portholes are tiny, thick acrylic plastic, several inches thick, conical shape, wider on the outside than inside. This shape helps the pressure push the window into its frame. The more pressure, the tighter the seal. The ocean actually helps keep the window in place. Looking through these portholes into the abyss is otherworldly. At 20,000 feet, it's completely dark. No sunlight reaches that deep. The submersible's lights illuminate only a small area. Beyond that circle of light is infinite blackness. You see strange creatures, fish with huge eyes, transparent bodies, bioluminescent organs that glow, life adapted to eternal darkness and crushing pressure. The deepest anyone has ever gone is the Mariana Trench. In 1960, Jacques Piccard and Don Walsh descended in a submersible called the Trieste. They reached the bottom, 35,114 feet. They spent 20 minutes there. The pressure was over 16,000 pounds per square inch, 8 tons per square inch. The Trieste used different design. Its pressure sphere was attached to a large float filled with gasoline. Gasoline is lighter than water and doesn't compress under pressure like air does. The float provided buoyancy. To descend, they carried iron pellets as ballast. To ascend, they released the pellets. Simple and reliable. At the bottom of the Mariana Trench, they saw something surprising. A flatfish, a living creature at the deepest point on Earth. This proved that life exists everywhere in the ocean. No depth is too extreme. Life finds a way. In 2012, filmmaker James Cameron made a solo dive to the Mariana Trench. He stayed longer than Piccard and Walsh. He filmed and collected samples. His submersible, the Deep-Sea Challenger, was built from special foam that could withstand the pressure. The whole vehicle was long and narrow, like a torpedo standing upright. These extreme depth dives are rare. They're expensive, they're risky, but they teach us about the limits of engineering. Each dive pushes materials science forward. We learn what works under pressure. We develop new alloys, new designs, new techniques. The pressure at extreme depths does strange things. It changes the properties of materials. Wood becomes waterlogged and heavy. Styrofoam compresses into dense pellets. Air spaces collapse. Even the water itself becomes denser. Slightly, but measurably denser than surface water. Deep-sea submersibles move slowly. They're not streamlined for speed. They're built for strength. Their movements are deliberate. Rising and sinking is controlled by ballast. Moving horizontally is done with small thrusters. Everything is gentle. No sudden movements, no rushing. The silence at depth is profound. The submersible's equipment hums quietly. Otherwise, nothing. No waves, no surface noise, just the pressure of miles of water above you, the weight of the ocean pressing down. Scientists who dive in research submersibles describe it as meditative. The slow descent, the darkness, the strange beauty of deep sea life, the knowledge that you're in a place very few humans have ever been. It changes your perspective, makes you realize how little we know about our own planet. Most of the deep ocean remains unexplored. We've mapped the surface of the Moon and Mars in more detail than we've mapped our ocean floor. Deep-sea submersibles are slowly changing that, dive by dive, discovery by discovery. These submarines prove that depth is not a barrier. Pressure is not a limit. With the right design, the right materials, the right preparation, humans can go anywhere, even to the deepest, darkest places on Earth. But whether diving to extreme depths or cruising at moderate depths, all submarines share certain challenges. One of the most basic is something we take for granted on land: temperature. The ocean at depth is cold, very cold. Below a few hundred feet, the temperature drops to just above freezing, around 2 to 4 degrees Celsius. That's 35 to 39 degrees Fahrenheit. Cold enough that you'd get hypothermia in minutes if you were in the water. A submarine's hull sits in this cold water. The outside of the hull becomes freezing cold. Touch it from the inside, and it feels like touching ice. In some spots, condensation forms. Water droplets appear on the cold metal. They drip down, collect in puddles. The submarine weeps, but inside the submarine it's warm, too warm sometimes. All the machinery generates heat. The reactor or diesel engines produce heat. Electronics produce heat. 100 human bodies produce heat. Each person generates about 100 watts of heat just by existing. That's like having 100 light bulbs burning inside the submarine. This creates a problem. The heat has nowhere to go. The submarine is sealed, no windows to open, no breeze. The heat accumulates. Without cooling systems, the temperature inside would climb until it became unbearable. Submarines use seawater to cool themselves. They pump cold seawater through heat exchangers. These are devices with thin metal walls. Hot water from the submarine's cooling system flows on one side. Cold seawater flows on the other side. Heat transfers through the metal. The hot water cools down. The cold seawater warms up. Then, the warmed seawater gets pumped back outside. It's like having the ocean as your air conditioner, an infinite supply of cold water. As long as the pumps work, you can cool anything, but this creates interesting situations. The submarine's hull is cold on the outside and warm on the inside. Just a few inches of steel separate freezing water from warm air. The temperature gradient is extreme. This causes condensation. Moisture in the air touches the cold hull and turns to water, like how a cold glass of water sweats on a hot day. Submarines have to manage this condensation. If water drips onto electronics, things short-circuit. If it pools in corners, things rust. So submarines have insulation on the inside of the hull. This keeps the warm air from directly touching the cold metal. But insulation isn't perfect. Cold spots still develop. Condensation still forms. Crew members learn which areas are cold, which spots drip. They avoid storing sensitive items there. They place drip pans to catch the water. It's a constant battle against the temperature difference between inside and outside. Temperature affects everything. Batteries work poorly when cold. Electronics have optimal temperature ranges. Too hot, and they malfunction. Too cold, and they slow down. Submarine designers have to plan for this. Each piece of equipment needs to stay within its temperature limits. The reactor compartment is the hottest area. Nuclear reactors generate enormous heat. Even with cooling systems running, the reactor space stays warm. Workers there wear lighter clothing. They take frequent breaks. The heat is oppressive. Other parts of the submarine can be chilly. Areas far from heat-generating equipment. Areas near the outer hull. Crew members in those spaces might wear jackets. Just 20 feet away, in the engine room or reactor space, people are sweating. This temperature variation is hard on the body. You move from hot spaces to cold spaces throughout your shift. Your body never quite adjusts. You're always too hot or too cold. Never quite comfortable. Some submarines have better climate control than others. Newer submarines have sophisticated HVAC systems. Heating, ventilation, and air conditioning. They can maintain different temperatures in different compartments. Keep the sleeping areas cool. Keep the work areas comfortable. But older submarines have simpler systems. Less control, more variation. Humidity is also a challenge. All those human bodies breathing, cooking food, washing. Everything adds moisture to the air. Too much humidity and things mold. Condensation becomes worse. People feel sticky and uncomfortable. Dehumidifiers run constantly. They pull moisture from the air. The water collects in tanks or gets pumped overboard. But they can't catch everything. High humidity is a fact of submarine life. You learn to live with it. Your clothes never fully dry. You hang your laundry and it stays damp, a bit clammy. Eventually, you put it on anyway, because everything is equally damp. After a few weeks, you stop noticing. Your baseline for dry adjusts. The cold hull does provide one benefit. It helps cool hot equipment quickly. If something overheats, you can position it near the hull. The cold metal pulls heat away. It's an emergency cooling method that has saved equipment more than once. The temperature difference also affects sound. Remember how submarines need to stay quiet. Temperature layers in the water create acoustic effects. Warmer water on top, colder water below. Sound bends at these boundaries. Submarines use this to their advantage. They position themselves in specific temperature layers to hide from sonar. The ocean's temperature is not uniform. It varies by depth, by location, by season. Submarines moving through these temperature zones have to constantly adjust. Their cooling systems work harder in warm tropical water. They work less in cold Arctic water. Inside the submarine, maintaining comfortable temperature is about balance. Remove too much heat and people get cold. Remove too little and people overheat. The goal is that narrow, comfortable zone. Not too hot, not too cold, just right. But achieving just right in a sealed steel tube surrounded by freezing water is harder than it sounds. It requires constant attention, constant adjustment. The submarine breathes heat in and out, managing the thermal exchange between its warm living crew and the cold dead ocean outside. Radio waves don't travel through water well. They bounce off the surface. They get absorbed by salt. Go just a few feet underwater and radio signals disappear. This makes communication with submarines difficult. On land, you can talk to anyone, anywhere, instantly. Pull out your phone and call across the world. But submarines are cut off, separated from the surface world by an invisible barrier. They're alone in a way few people ever experience. Very low-frequency radio can penetrate seawater. VLF radio uses enormous wavelengths, waves that are miles long. These waves can reach submarines at shallow depths, maybe 50 or 100 feet down. But VLF transmits data incredibly slowly, a few characters per minute, sometimes less. Imagine sending a text message, and it takes an hour to transmit. That's VLF. It's useful for short, critical messages. 3 words: surface immediately, or proceed as planned. But you can't have conversations. You can't send detailed information, just brief commands. To receive VLF, submarines trail a long antenna behind them, a wire that stretches out hundreds of feet through the water. The submarine moves slowly to avoid tangling it. They listen for signals from transmitters on land, massive transmitters that require enormous amounts of power. The transmitting antennas themselves can be miles across. The US Navy used to have VLF transmitters in Wisconsin. The antenna wires stretched across entire valleys. These transmitters could reach submarines anywhere in the world's oceans, but running them cost millions of dollars. They needed so much power that they had their own power plants. For faster communication, submarines need to get closer to the surface. They can raise a communications mast, a thin pole that extends above the surface while the submarine stays below. The mast has antennas for satellite communication, normal radio, data transmission. Raising the mast is risky. It breaks the surface. Radar can detect it. Visual observers might spot it. So submarines only raise their masts when necessary. They stay at periscope depth, just below the surface, get their messages, then descend again quickly. The messages are brief. Familygrams from home, short updates from command, news summaries, everything compressed into the minimum necessary information. Submarines receive data downloads, emails, weather updates, intelligence reports. They process it all in minutes, then back down to depth. Sending messages works the same way. The submarine composes messages throughout the day, stores them, then, during the brief mast-up time, transmits everything in a burst. A few seconds of transmission, then silence again. Some deployments have no communication at all. Strategic submarines carrying nuclear missiles maintain complete radio silence. They don't want anyone to know where they are. They don't transmit. They receive only on VLF, just listening for the signal that hopefully never comes. These crews go months without talking to family. No phone calls, no emails, no letters, complete isolation. They knew this when they volunteered, but knowing doesn't make it easier. You miss birthdays, anniversaries, important events. Your family celebrates without you. Life continues on the surface, and you're not part of it. When submarines do get messages from home, they're carefully screened. Bad news is held back until the submarine is about to return to port. Learning about a family emergency when you're 2 months from home and can't do anything about it is cruel. So, the Navy filters the messages. Only positive news gets through. Crew members understand this. They know the messages they receive might not tell the whole truth. They trust the system, but they wonder, is everything really okay at home? Or are they being protected from something? This uncertainty adds to the stress. The isolation affects people differently. Some find it peaceful. No news means no worries. They focus on their job. They live in the present moment. The submarine becomes their entire world. What's happening on the surface doesn't matter because they can't do anything about it. Others struggle. They feel cut off. They miss their families intensely. They count the days until they can surface and make contact. The isolation weighs on them. It's one of the main reasons some people leave submarine service. The separation is too hard. Communication between submarines is also limited. Underwater, they can't talk to each other easily. Acoustic communication exists, but it's slow and can be detected. So, submarines operate independently, each one alone in its section of ocean. This loneliness is profound. You're in a vessel with 100 other people, but your vessel is isolated from every other vessel, from every port, from every land station. You're together, but alone. A small community, adrift in emptiness. The radio operator's position is crucial. They manage all communications. They receive the VLF signals. They operate the masts. They encode and decode messages. They're the submarine's link to the outside world, the one thread connecting you to home. Sometimes that thread feels very thin, a message that takes hours to arrive, a brief satellite connection that lasts seconds, then nothing, back to silence, back to isolation, back to the deep where no signals reach and no voices call. This silence becomes normal. After weeks underwater, you forget what it's like to hear from the outside world. The submarine is reality. Everything else feels distant and dreamlike. Home becomes an abstract concept, a memory, a place you'll return to eventually, but that doesn't feel real right now. Yet humans adapt. We're social creatures, but we can handle isolation when necessary. Submarine crews create their own community. They talk to each other. They share stories. They build bonds. The submarine becomes a village, small and isolated, but complete unto itself. And in that isolation, something interesting happens. Time starts to behave strangely. There is no sunrise on a submarine, no sunset, no moon rising, no stars appearing at dusk. Time stops being something you feel and becomes something you track. A number on a clock, an abstract concept. Your body expects a 24-hour cycle. Millions of years of evolution built this expectation into your cells. Light appears and disappears in a rhythm. Your body follows that rhythm. When light fades, you get sleepy. When light returns, you wake up. This is your circadian rhythm, your biological clock, but submarines operate on artificial schedules. Remember the 18-hour day some submarines use? 6 hours on watch, 12 hours off watch. This makes operational sense. It divides the crew into 3 shifts. Each shift covers 8 hours of the day. Efficient. But your body doesn't care about efficiency. Your body wants 24 hours. When you force it into 18-hour cycles, something breaks. You're perpetually jet-lagged, never quite adjusted. Your sleep suffers. Your mood suffers. Your body chemistry goes slightly wrong. Some submarines use 24-hour days, but with unusual schedules. You might work midnight to 6 a.m., then again from noon to 6 p.m. Split shifts. Your sleep gets fragmented. You sleep in chunks. 4 hours here, 3 hours there. Never a full night's rest. The artificial lighting doesn't help. Fluorescent lights that never change brightness. They're always on at the same intensity. No dawn, no dusk. No gradual transitions. Just on or off. Your brain doesn't get the light cues it needs to regulate sleep. After a few weeks, your sense of time becomes elastic. Days blend together. Was that yesterday or 3 days ago? You lose track. The monotony erases markers. Tuesday feels like Thursday. Morning feels like evening. Time becomes a fog. Some crew members adapt better than others. Young people with flexible circadian rhythms adjust more easily. Older crew members with more rigid internal clocks struggle. But everyone experiences some disorientation. It's unavoidable. The lack of natural time markers affects memory too. You remember events, but not when they happened. Did that equipment failure happen last week or 2 weeks ago? You're not sure. The events exist in your memory as a sequence, but without timestamps. Like a story where you know what happened, but can't say when. Holidays become important. They're markers, fixed points in time. Thanksgiving, Christmas, New Year's. These days have meaning. The crew celebrates them with special meals, decorations, traditions. These celebrations anchor time. They give structure to the blur. Birthdays matter too. The crew makes a fuss over birthdays. Cake, if possible. Singing. Small gifts. It's a way to mark someone's personal time, to acknowledge that they're another year older, even though time feels suspended down here. The submarine keeps official time, usually Greenwich Mean Time or Zulu time, but this time might not match local time at the submarine's actual location. You could be off the coast of Japan, but running on Atlantic time. So the clock says 3 a.m., but outside, if you could see the sun, it would be afternoon. This disconnect between official time and natural time adds to the strangeness. Your schedule says it's time to sleep, but your body knows the sun is up somewhere above you. Or you're starting your workday, but the world is going to bed. You exist out of phase with the planet. Sleep quality suffers. The constant noise doesn't help. Ventilation systems humming, pumps running, distant machinery. It's not loud, but it's constant. Your brain never gets true silence. Some people can't sleep without white noise after submarine service. The silence of a normal bedroom feels wrong. The beds are uncomfortable, narrow, hard mattresses. You're constantly getting in and out as shifts change. The sheets never feel fresh. The pillow feels flat. You're never quite comfortable. Sleep becomes something you do because you have to, not because it feels good. Dreams become vivid. Maybe it's the stress. Maybe it's the disrupted sleep cycles. Maybe it's the isolation. But submarine crews report intense dreams. Dreams about the surface. Dreams about home. Sometimes nightmares about floods or being trapped. The subconscious processing the environment you're in. Some people start to feel like time outside has stopped. Like the world is frozen while they're underwater. They know intellectually that life continues. People are working, going to school, getting married, having babies. But it doesn't feel real. It feels like everyone is on pause, waiting for the submarine to surface. This creates a strange sense of timelessness. You're not really part of the regular world. You exist outside normal time. In a bubble where days don't matter and dates are arbitrary. Work shifts are your reality. Wake, work, eat, sleep, repeat. The cycle continues regardless of whether it's Monday or Friday, January or June. Veterans of submarine service describe it as living in a time warp. Months underwater feel both longer and shorter than they should. Longer because each day drags. Shorter because looking back, the whole deployment feels like a blur. Time compressed and expanded simultaneously. This temporal distortion is one of the strangest aspects of submarine life. Not dangerous, not painful, just deeply weird. Your relationship with time changes. You stop trusting your sense of it. You rely on clocks and schedules completely. Your internal sense of time becomes unreliable. When you finally surface after months underwater, the world has moved on without you. Technology has changed. News has happened. People's lives have progressed. You step back into normal time and have to catch up. Have to relearn how days work. How to trust that tomorrow will come after today in a predictable rhythm. But while you're down there, time is just a number, a watch position, a meal schedule, something external to you rather than something you feel in your bones. Everything on a submarine is designed 3 times. 3 pumps, where 1 would do. 3 ways to control depth. 3 power sources. 3 methods for everything critical. This is called redundancy. It's the reason submarines survive. Things break. Equipment fails. Murphy's Law applies underwater just like everywhere else. But on a submarine, you can't call for help. You can't wait for a repair crew to arrive. You are the repair crew, and you're hundreds of miles from the nearest port. So submarines carry spare parts for everything. Warehouses worth of components packed into tiny storage spaces. Pumps, valves, circuit boards, seals, cables. If it can break, there's a replacement somewhere on board. Finding it might take time, but it's there. Every crew member trains for emergencies. Fire drills, flooding drills, reactor emergency drills, loss of power drills. They practice until the responses become automatic. Because in a real emergency, you don't have time to think. You have to act. Fire is one of the worst emergencies. In an enclosed space with limited air, fire is devastating. Smoke has nowhere to go. It fills compartments. People can't breathe. The submarine has sophisticated fire suppression systems. But ultimately, humans have to fight the fire. Crew members in the affected compartment wear breathing masks, emergency air supplies. They attack the fire with extinguishers, chemical foam, CO2 systems. The submarine has multiple types of fire suppression. Different fires need different approaches. Meanwhile, other crew members seal off the compartment, close the hatches, isolate the fire. This is brutal but necessary. If the fire spreads, the whole submarine is at risk. So, they contain it. Lock it in one space, even if people are still in that space. Flooding is equally dangerous. A crack in the hull, a failed seal, water spraying in under tremendous pressure. At depth, water comes in like a cutting torch. The pressure is so high that the stream can slice through clothing and flesh. The response is immediate. Find the leak. Patch it. Use emergency patches, wooden wedges, rubber seals, whatever stops the water. While some crew members patch the leak, others pump out the water that's already entered. Pumps working at maximum capacity. If they can't stop the leak, they seal the compartment. Close the watertight doors. Abandon the flooded space. Let it fill completely. The submarine can survive with some compartments flooded. It's designed for this. Lose one section, but save the rest. These decisions happen in seconds. No time for committees or discussions. The damage control officer makes the call. Close the hatch. Seal the compartment. Move on. It sounds cold, but it's survival. Save the ship or lose everyone. Submarines drill these scenarios constantly. Not just the procedures, but the mentality. The willingness to make hard choices under pressure. The ability to stay calm when everything is going wrong. This is why submarine crews train so intensively. Every crew member knows multiple jobs. Cross-training is standard. If the primary person for a critical system is injured or in a flooded compartment, someone else can take over. Everyone learns basic damage control, basic firefighting, basic first aid. You're a team, and every member has to be versatile. The culture emphasizes staying calm. Panic kills. In an emergency, voices stay level. No shouting unless absolutely necessary. Clear communication. Short sentences. Confirm every instruction. Close valve 7. Closing valve 7. Valve 7 closed. Precision matters. Medical emergencies are challenging. The submarine has a small medical facility, usually a corpsman or medic, not a full doctor. They can handle minor injuries, broken bones, cuts, illnesses, but serious medical emergencies are risky. If someone needs surgery or intensive care, the submarine has to surface. They radio for help. A helicopter might evacuate the patient. Or they head to the nearest port at maximum speed. But this takes time. Hours. Sometimes days. The medic does what they can with limited resources. Submarines carry extensive medical supplies, drugs, surgical tools, diagnostic equipment. The medic trains constantly. They study. They practice. They prepare for situations they hope never happen. It's lonely being the only medical professional on board. Tremendous responsibility with no one to consult. Psychological emergencies happen too. Someone breaks down, can't handle the stress, can't handle the isolation. This is rare because submarine crews are screened carefully. But it happens. The crew has protocols. Keep the person safe. Keep them away from critical systems. Provide support. Get them off the submarine as soon as possible. The submarine community is small and tight-knit. Everyone knows everyone. If someone is struggling, others notice. They check in. They offer support. Mental health is taken seriously because everyone's safety depends on everyone else being functional. Trust is absolute. You trust your crewmates with your life. Literally. You trust that they'll do their jobs correctly, that they'll follow procedures, that they'll stay calm in emergencies. This trust builds over months of living and working together in impossibly close quarters. When something goes wrong, the crew works as one organism. No hesitation, no doubt. Everyone knows their role. Everyone executes. The submarine has survived 60 years of operations with remarkably few disasters. This success comes from training, redundancy, and a culture that prioritizes safety above everything. But the best emergency is the one that never happens. Prevention is the real goal. Constant maintenance, constant inspection, constant vigilance. Catch problems before they become emergencies. Fix wear before it becomes failure. This preventive mindset permeates submarine operations. Nothing is ignored. Every unusual sound is investigated. Every small leak is traced and repaired. Every system is monitored continuously. The goal is boring, uneventful, routine. Because exciting days on submarines are often bad days. And through all of this, through all the preparation and drilling and vigilance, the submarine maintains its mission, moving through the deep, staying hidden, accomplishing its objectives while keeping its crew safe. The ocean is patient. It waits for mistakes. But submarines don't make mistakes often. And when they do, they're prepared. Submarines try to be invisible, silent, undetectable. But nature doesn't care about their intentions. Life finds submarines and makes them home. When a submarine sits in port, even for a few days, things start to grow on the hull. Algae appear first. Microscopic plants that attach to any surface in water. They're green or brown. They form a thin film. You wouldn't notice it at first, but it's there, growing, spreading. Then come the barnacles. These strange creatures are related to crabs and shrimp, but they don't swim. They attach to surfaces permanently. A barnacle larva floats in the water until it finds a good spot. Then it glues itself down, head first. It builds a hard shell around itself, and there it stays for the rest of its life. Barnacles on a submarine hull create problems. They add weight. A large submarine can accumulate tons of barnacles and other growth. Literally tons. This extra weight affects the submarine's balance. Its buoyancy calculations become less accurate. Barnacles also create drag. They make the hull rough instead of smooth. Water flowing past the hull encounters resistance. The submarine has to work harder to move. It uses more fuel. It goes slower. And worse, the rough hull creates turbulence. Turbulence makes noise. The quiet submarine becomes louder. Other things grow too. Mussels attach themselves. They're similar to barnacles, but with different shells. Seaweed can take hold in port. Long strands that wave in the current. Small crustaceans find homes in the growth. Then fish come to eat the crustaceans. The submarine becomes a reef, a traveling ecosystem. This happens faster in warm water. Tropical ports see heavy growth in days. Cold water slows things down but doesn't stop them. Life is persistent. It exploits every opportunity. A submarine hull is real estate. Stable. Solid. Life claims it. Submarines use anti-fouling paint to slow this growth. Special coatings that resist attachment. Some paints contain copper compounds that are toxic to barnacles and algae. Others use slick surfaces that organisms can't grip. But nothing works perfectly. Growth still happens, just more slowly. Hull cleaning becomes necessary. When a submarine returns to port after deployment, divers inspect the hull. If there's significant growth, they clean it. Scrapers remove barnacles. Brushes scrub away algae. It's hard physical work. The barnacles are glued on tight. Some have to be chiseled off. Dry dock cleaning is more thorough. The submarine enters a dry dock. Water pumps out. The hull emerges into air. Now, workers can really clean it. Pressure washers blast away growth. Scrapers get every barnacle. Then they repaint. Fresh anti-fouling coating. The submarine goes back to being smooth and clean. But the cycle repeats. As soon as the submarine enters water, life begins attaching again. It's an endless battle. The submarine wants to stay clean. Life wants to colonize. Neither side wins permanently. It's a stalemate that favors life slightly. Submarines at sea collect less growth than submarines in port. Moving water makes attachment harder, and submarines spend much of their time at depths where few organisms exist. The deep ocean is too cold and dark for most life. Below a few hundred feet, there's not much trying to attach. But even at depth, some organisms might hitch rides. Tiny things that can survive pressure and cold. They hide in crevices, in the gaps between hull tiles. These stowaways travel with the submarine. When it surfaces in a new port, they might spread to local waters. Invasive species transported by submarines. It's rare, but it happens. The irony is beautiful. Submarines are some of the most advanced technology humans have created. Cutting-edge engineering. But they can't escape biology. Can't escape the fundamental drive of life to spread and colonize. A submarine coated in barnacles is nature's reminder that we're not separate from the living world. We're part of it. Some submariners see their hull growth as a badge. It shows they've been at sea, working, operating, not sitting in port. Fresh paint means you're new, or you've been idle. A hull with character means you've been out there doing the job. Others hate it. They see it as undisciplined. A well-maintained submarine should be clean. Growth means you've let standards slip. This tension exists in every navy. Is some barnacle growth acceptable? Or should submarines be spotless? Practically, excessive growth is a problem. It must be addressed. But a little growth? Maybe that's just the submarine showing where it's been, the places it's visited. Each barnacle is a souvenir, a mark of passage through waters where that barnacle species lives. Scientists can study submarine hulls to learn about ocean life. What species are present in different regions? How are species spreading? Are invasive species using military vessels as transport? Submarine hulls become unintentional research platforms. The ecosystem on a hull is temporary. It exists only as long as the submarine tolerates it. Eventually, cleaning happens. The ecosystem gets scraped away. The organisms die. But they're replaced quickly. New larvae attach. New growth begins. The cycle continues. This persistence of life is humbling. Humans build vessels to conquer the ocean, to move through it secretly, to control their environment completely. But the ocean doesn't acknowledge this control. Life does what life does. It grows. It spreads. It finds a way. A submarine at depth, moving silently through darkness, might seem isolated from the living world. But look closely at its hull, and you'll find passengers. Tiny organisms clinging on, living their lives on this moving island, unaware and uncaring that they're riding on one of humanity's most sophisticated machines. Even in our attempts at isolation, we carry life with us. Without rituals, time becomes meaningless. Without traditions, every day is the same. Submarines understand this. They create structure through ceremony. Small rituals that mark time and give meaning to the endless routine. Crossing the equator is a big one. When a submarine crosses from the northern hemisphere to the southern hemisphere, or vice versa, they hold a ceremony. It's called the line crossing ceremony. Those who've crossed before are called shellbacks. Those crossing for the first time are polywogs. The ceremony involves challenges, tests, silly rituals that everyone knows are silly but participates in anyway. Polywogs might have to crawl through foam or answer ridiculous questions. It's uncomfortable and embarrassing. But at the end, you're a shellback. You've earned your place. This might seem juvenile, but it serves a purpose. It marks an achievement. It creates a shared experience. Everyone who crosses the equator remembers their ceremony. It bonds the crew, gives them stories to tell, makes them part of a tradition stretching back centuries. Other lines matter too. The Arctic Circle, the International Date Line. Each crossing can have its own ritual, its own recognition. These geographic markers become important because they're the only landmarks submarines encounter. No mountains, no buildings, just invisible lines on charts that sailors give meaning to. Holidays are celebrated with intensity. Christmas gets full treatment. Decorations appear throughout the submarine. Crew members string lights, put up small trees, create festive atmosphere in the steel tube. The galley prepares special meals. Turkey or ham, desserts, the best food they can manage. Someone always plays Santa, distributes small gifts, candy, snacks, items from care packages. It's not about the gifts themselves. It's about maintaining connection to the holiday, acknowledging that Christmas exists even underwater, that the submarine crew is still part of the world celebrating above. Thanksgiving happens underwater too. A full traditional meal. The cooks work hard to make it special. Real mashed potatoes if possible. Cranberry sauce, stuffing. Crew members eat together, share what they're thankful for. Usually it's simple things. Health, safety, shipmates, the chance to serve. Birthdays matter enormously. On the surface, birthdays are personal. But on a submarine, they're communal events. The whole crew acknowledges your birthday, sings to you, shares cake or whatever dessert is available. You're embarrassed, but also touched. These people care enough to celebrate you. Some submarines have unique traditions, specific to that boat. Maybe a particular phrase everyone says at shift change. A ritual with the submarine's mascot. A special meal on the anniversary of the submarine's commissioning. These traditions give the submarine identity, make it more than just a numbered vessel. The submarine's name matters too. It's not just USS followed by a number. It's usually named for something meaningful. A state, a city, a famous person, a historical battle. The crew takes pride in this name. They learn its history. They feel connected to whatever or whoever the submarine honors. Qual cards are another ritual. When new crew members join, they start working on qualifications, learning every system on the submarine. They carry a qualification card, get signatures from experts on each system after demonstrating knowledge. It takes months, sometimes over a year. Earning your dolphins is the culmination. Dolphins are the submarine warfare insignia, a pin showing 2 dolphins flanking a submarine. You wear it on your uniform. It means you're qualified. You know the submarine. You can be trusted. The ceremony when you receive your dolphins is significant. The captain pins them on you in front of the crew. Everyone watches. Everyone claps. You've joined the brotherhood. You're no longer a newcomer. You're a qualified submariner. This moment stays with you forever. Some crews have pranks, good-natured tricks played on each other, hiding someone's shoes, switching name tags, short sheeting beds. These pranks relieve tension, create laughter, build camaraderie. As long as they don't interfere with operations, they're encouraged. Humor keeps people sane. Movie nights happen when possible. The crew gathers in a common space, watches a film on a screen. It's like going to the theatre, except you're hundreds of feet underwater. The movie choice matters. Usually something light. Comedies are popular. Action films. Nothing too heavy or depressing. Some submarines hold talent shows. Crew members perform, play instruments, tell jokes, do magic tricks. The quality doesn't matter. It's about participation, about seeing your shipmates in a different context. The weapons officer who plays guitar beautifully, the sonar operator who does impressions. These hidden talents emerge. Food becomes ritualistic. Pizza night, Taco Tuesday, Hamburger Day. These recurring meals mark the week, give structure to time. You know what day it is by what you're eating. When every day feels the same, these small differences matter. The crew might create competitions. Who can do the most push-ups? Who knows the most trivia? Who can solve a puzzle fastest? Friendly rivalries develop. People make bets. Nothing serious. Usually candy bars or desserts. But the competition adds spice to routine. Watch relief is ritual. When your shift ends, someone relieves you. There's a formal turnover. You brief them on the status of everything. They acknowledge you're released. This handoff happens thousands of times during a deployment. Always the same way. The ritual ensures nothing is forgotten, no information lost. Morning routine has its own rhythm. Wake up, brush teeth, get coffee, eat breakfast, report to your station. Everyone follows similar patterns. These patterns become comforting, predictable. In an environment where so much is controlled centrally, these personal routines give you agency. Some crew members bring traditions from home. A lucky charm, a photo ritual, prayer practices. The submarine accommodates these personal traditions. They're not standardized, but they're respected. Everyone needs something that connects them to their life outside. These rituals and traditions don't just mark time. They create meaning. They make the submarine more than machinery. They make it a community, a place where humans live together and support each other through the strange experience of living underwater for months at a time. The order comes. Surface, head to port. The deployment is ending. You're going home. The crew feels it immediately. The mood shifts. Excitement builds. After months underwater, you're about to see the sky again. The submarine rises slowly from depth. Up through the dark water. Up through temperature layers. Up toward the light. As you approach the surface, you can hear changes in the sounds around you. The ocean sounds different near the surface. Waves. Wind. The distant rumble of ships. Then the submarine breaks through. The sail emerges first. Water streams off it. Then the rest of the hull. The submarine bobs gently in the waves. After months of stillness at depth, the motion feels strange. The submarine rocks. People lose their balance. Your inner ear has forgotten how to handle surface movement. Hatches open. Fresh air rushes in. Real air. Not recycled. Not filtered. Air that smells like salt and ocean. Air that's been outside. Crew members crowd near the hatches. They want to feel it, to breathe it. Some people close their eyes and just inhale deeply. The first crew members go topside. They climb out onto the deck, and they see it, the sky. It's overwhelming. So much space, so much light. The sky goes on forever in every direction. After months in enclosed spaces, the openness is shocking. The sun is incredibly bright. Even on cloudy days, it's bright. Your eyes have adapted to artificial light. Weak fluorescent bulbs. Now you're looking at the actual sun. It hurts. You squint. You look away. Your eyes water. But you keep trying to look because you've missed it so much. Colors are more vivid than you remember. The blue of the water. The grey of clouds. If there's land nearby, the green of trees. Your brain has been seeing metal grey and artificial white for months. Natural colours seem supersaturated, almost fake, like someone turned up the saturation on reality. Sounds are overwhelming too. Wind, waves, birds if you're near land. The sounds are chaotic, unpredictable. You've been living with constant predictable noise, machinery humming at steady frequencies. Now everything is random. Wind gusts, waves splashing, seabirds calling. Your brain doesn't know how to process it all. The space is disorienting. You can see for miles. The horizon stretches out. There are no walls, no ceiling, just open space in every direction. Some people feel awe. Others feel exposed, vulnerable, like something could come from any direction. The submarine's enclosed safety feels far away. The motion sickness hits some people. On the surface, submarines roll and pitch with the waves. After months of steady hovering at depth, this motion makes people queasy. They go back inside, down to spaces that don't move as much. Wait for the nausea to pass. The transit to port takes hours or days. During this time, crew members adjust. They spend time topside in shifts, getting used to the sky gradually, learning to trust their eyes again, remembering how to navigate by visual landmarks instead of instruments. Approaching port, they see civilization, buildings, cars, people on shore. It looks alien, like a different world. You've been gone only a few months, but it feels like years. Everything looks smaller than you remember, or bigger. Your sense of scale is broken. The submarine pulls into port. Lines are thrown. The submarine ties up to the pier. The crew sees families waiting. Wives, husbands, children, parents. Everyone is waving, crying, excited. The crew waves back. Some people are crying too. Then they can disembark, walk down the gangway, step onto solid ground. The the ground doesn't move. After months on a submarine, even stable ground feels strange at first. You walk like you're still on a moving deck. Your gait is unsteady. People call it getting your land legs back. Families rush forward. Hugs, kisses, reunions. Small children who barely remember their parent. Toddlers who've grown. Everyone talking at once. So much noise. So many voices. After the controlled quiet of the submarine, it's chaos. Beautiful chaos, but overwhelming. Going home is strange. Your house feels huge. So much space. You can walk more than 10 feet in any direction. Rooms have windows. Natural light. You open and close windows because you can. Because air can come in from outside. This simple thing feels miraculous. The shower is different. Unlimited hot water. You can stand there for 20 minutes if you want. No one timing you. No one waiting for their turn. You use too much water and don't care. It's excessive and wonderful. The bed is so soft, so wide. You spread out, move around. The sheets smell like home detergent. Not submarine. You lie there, feeling the stillness, the quiet. No machinery humming. No ventilation noise. The silence is almost too quiet. Some submariners run fans at night. Need the white noise to sleep. Food tastes different, fresher, more varied. You can go to a restaurant, order whatever you want. The choices are overwhelming. The menu has 50 items. You're used to eating whatever was prepared. Now you have to decide. It's paralyzing. You pick something simple. Crowds are difficult. The grocery store has too many people. Too much movement. Too many choices. You stand in the cereal aisle, staring at hundreds of options. You can't decide. There are 20 kinds of the same cereal. Your brain can't process it. You grab one randomly and leave. Driving feels dangerous. Everything moves so fast. Cars zipping past. You grip the wheel too tight. Jump at sudden movements. Your reflexes are off. Your spatial awareness is calibrated for narrow submarine corridors. The open road feels chaotic. Sleep is disrupted. You wake at odd hours. Your body is still on submarine time. Still expecting 18-hour days. Still listening for the sounds that mean something is wrong. You lie awake in the darkness, listening to nothing, trying to adjust. It takes weeks to fully readjust. To remember how to live on land. How to be part of the surface world. How to relate to people who haven't lived underwater for months. How to explain where you've been without being able to talk about most of what you did. Eventually you adapt. The submarine fades slightly, becomes a memory, but part of you stays down there. Always. You dream about it sometimes. The narrow spaces, the red lighting, the sounds. And sometimes, strangely, you miss it. Submarines are impossible. They shouldn't work. Humans aren't meant to live underwater. We can't breathe water. We can't withstand pressure. We can't see in the dark. We're land creatures, air breathers, dependent on light and space and sky. Yet we go anyway. We build steel tubes. We seal ourselves inside. We sink into the deep. And we live there, for months, contentedly, productively. We turn the impossible into routine. This tells us something profound about being human. We're not limited by our biology. We're limited only by our imagination and our will. When we want to go somewhere, we find a way. Even if that somewhere is beneath the ocean. Even if everything about our bodies says we don't belong there. Submarines prove we're adapter creatures. We can adjust to almost anything. Give us time and we'll make any environment feel normal. The cramped spaces, the recycled air, the constant noise, the artificial time. All of it becomes ordinary. Our baseline shifts. What seemed unbearable at first becomes home. This adaptability is our superpower. It's why humans live everywhere on Earth. Deserts, mountains, Arctic ice. We're not particularly fast or strong or resilient, but we're flexible. We change ourselves and our environment until we fit. And submarines are the ultimate expression of this, creating an environment where none should exist. Submarines also teach us about community. You can't survive alone underwater. You need your crew. You depend on them, absolutely. They depend on you. This mutual dependence creates bonds stronger than almost anything else. Submariners talk about their crews like family, because they are family. Chosen family, born from necessity and shared experience. In our normal lives, we can pretend we're independent. We can isolate, keep to ourselves. But submarines strip away that illusion. On a submarine, your survival depends on the person next to you doing their job correctly. And their survival depends on you. This creates trust at a level most people never experience. There's something beautiful about carrying your atmosphere with you. The submarine is a bubble of life, moving through an environment hostile to life. Inside the bubble, people breathe and eat and sleep and laugh. Outside is crushing pressure and freezing darkness. The boundary is just inches of steel, but those inches make all the difference. We're like this on Earth too, actually. Our planet is a bubble of life moving through the void of space. Thin atmosphere, magnetic field, just enough water and warmth. Outside, this bubble is vacuum and radiation and cold. We're all on a submarine called Earth. We just forget it because our submarine is so large. Submarines remind us of our fragility, how dependent we are on systems working correctly, on barriers holding, on constant vigilance and maintenance. Nothing maintains itself. Everything requires care and attention. The moment you stop monitoring, stop adjusting, stop fixing, things start to fail. But submarines also show our resilience. When things do fail, we adapt, we fix, we overcome. We've been operating submarines for over a century. Thousands of deployments. Millions of miles traveled underwater. The safety record is remarkable considering the risks. This is human ingenuity and dedication at its finest. The submarine is a metaphor for the human condition. We're all in enclosed spaces in some way. Our bodies are submarines for our consciousness. Our lives are bounded, limited. But within these limits, we create meaning. We build communities. We explore. We push boundaries, even while acknowledging them. And submarines show us that limitations breed creativity. The constraint of living in a steel tube forces innovation. Every system had to be imagined, designed, tested. Every problem required solutions. The limitations didn't stop progress. They directed it, made it focused, purposeful. Going underwater teaches humility too. The ocean is vast and powerful. It tolerates submarines, but doesn't care about them. One mistake and the ocean wins. This keeps submariners humble, respectful. They never forget they're visitors in an environment that could crush them instantly. There's peace in this humility, in accepting that you're small, that force is larger than you exist, that your survival requires working with others and respecting the environment. Modern life often encourages the opposite. Illusions of control, independence, invulnerability. Submarines cut through these illusions. Right now, while you rest comfortably wherever you are, submarines are gliding through dark water around the world. People are living in those steel tubes, breathing recycled air, seeing by sonar, eating from cans, sleeping in shifts, working quietly, existing in an impossible place, making it look ordinary through skill and teamwork and adaptation. They're proof that humans are explorers, not just of places, but of possibilities. What if we could breathe underwater? What if we could hide beneath the waves? What if we could create home anywhere we go? Submarines answer these questions. They say yes, we can. We do. We will continue. We build our bubbles of life and take them to impossible places. We adapt. We endure. We find peace in pressure. We learn to sleep in the gentle darkness beneath the weight of the world. We dream our dreams in the deep. And when we surface, we carry those dreams with us, changed by where we've been, grateful for what we've learned, ready to descend again when needed. This is what submarines teach us, that humans are remarkable, that we're capable of so much more than we think, that home isn't a place, it's the people we're with and the air we share and the trust we build, that we're all on submarines, all carrying our atmosphere through hostile environments, all depending on each other, all finding our way through the dark by staying calm, working together and never giving up. Sleep well, explorer. The deep will be here when you wake, peaceful and patient and full of wonders we're still discovering. Just like you. We've traveled deep tonight, you and I. From wooden eggs that barely worked to nuclear hearts that beat for decades. From breath-holding divers to crews living months beneath the ice. From silence to seeing with sound. From pressure to peace. You've learned how submarines sink and rise like breathing. How they navigate by listening. How they create their own air from the ocean itself. How people adapt to living in steel tubes, finding home in the most unlikely places. How life finds submarines, even when submarines try to hide. How humans carry their atmosphere with them wherever they go. These machines are marvels, but the real marvel is the people inside them, the ones who volunteer to seal themselves in darkness, who trust their lives to their crewmates completely, who find peace in pressure and comfort in routine, who prove that humans can thrive anywhere if we work together. If these quiet journeys bring you peace, consider subscribing. There are so many more wonders to explore together, always gently, always with curiosity. We'll discover more amazing things about our world, one peaceful story at a time. Leave a comment if you'd like. Tell me where you're listening from tonight. Are you near the ocean? Have you ever seen a submarine? What part of tonight's journey surprised you most? I'd love to hear your thoughts. Now, let these facts settle like a submarine finding its depth. Let them become part of your dreams. Your breathing can slow now, deep and steady like the ocean itself. In and out like ballast tanks filling and emptying, finding your perfect balance. You're safe in your comfortable spot, your own small bubble of peace. The world can wait until morning. Right now, there's only rest, only the gentle darkness, only the quiet. Somewhere tonight, a submarine glides through deep water. Its crew sleeps in shifts, rocked by gentle movement. They're dreaming their dreams beneath miles of ocean, peaceful in their steel home, finding rest in the deep. You can rest too. Let your thoughts grow quiet. Let your body grow heavy. Let sleep come naturally, the way a submarine finds neutral buoyancy. No effort, just release. The submarines will still be there tomorrow, still exploring, still teaching us what's possible, still proving that humans are remarkable creatures who can make home anywhere. But tonight, they're just part of your peaceful thoughts, gliding through your mind as you settle into sleep. Rest well, explorer. The deep will be here when you wake.